Yeah, I think it's one of those things. I think it's more one of those things. If you got like M, like you got like M. And I went to circus. Yeah, I call it one to go through there. More after one like this question. Yeah, I like this question. Oh, you took one? First semester of yeah, that's right. Hey, should I save you a seat?
I saved you a seat. No? I saved you a seat. So would 2:30 tomorrow work for you? Would that be a good time? So what you should do is come to my office in Corey, and I'll put you up there and make it happen, okay? Yep.
Once you have a Gucci suit, then I can wait. Then Jet came.
No one tells me.
He told me about his whole project from day one and how they had problems and how they overcame the problems.
All right. All right, good afternoon. Alrighty, so we have welcome to yet another review session, number 2. We have one more to go after this. So a couple of things to remind. Exam tomorrow is at 7 o'clock, and that's in 105 North Gate. So be there sharp. We're going to start right away at 7 p.m., not then after, so be aware of that. Let's see. The other thing is I got all the projects back, phase 1. I looked at them. I must say I'm generally impressed. We're probably going to try to get this thing ready together with the second midterm. So somewhere mid next week is when you can expect feedback on that. I will post project phase 2 tomorrow. I didn't want to do it before the midterm. I think you have plenty of things to do. So I also figured out that nobody would start working on the project before the midterm. So yeah, it's going to be posted tomorrow. And I'll give you about 2 weeks time for that afterwards. So that's still about, tomorrow's the, what is it, the 9th? 9th and 14th is the 23rd, is when phase 2 is due. And then the last phase is really going to be kind of implementing it. So keep an eye on that. With respect to the midterm, everything is the same as last time. It's a full open book exam, so don't forget your book, like people did, and don't forget your calculator. These are 2 things you have to bring, and then the rest you can bring all the other stuff you want to bring. But the most important thing, bring the book and the calculator. Don't forget that. Okay, so as I said, the material will mostly cover anything which came after midterm 1, which was basically we did everything in inverter, propagation delay. So it starts with power, and then it goes to complex logic. Really, it's an exam on complex logic, reading from combinational CMOS, pass transistor logic, ratioed logic, things like logical effort, and finally also dynamic logic and its kind of peculiarities. Okay, so that's what we're going to cover. So what I want to do today is again, yes. What? The midterm is at 7 o'clock sharp. 7 till 8:30. So people who take 122 should be able to make it in time. Okay. Sneak out of there a little bit early. Okay. Good. So we'll do the same thing like last time. I'm basically going to open the floor for questions. Going to rank order them a little bit, walk through them, and then we're going to go to one midterm. And the one I picked was one from 2002, which has some interesting questions in there. And as you will see, have some relevance to the questions we're going to be doing tomorrow. Okay? Sorry? Oh, yes, absolutely. Sorry. Forgot one thing. Obviously, adders is we handle it in class, so it's fair game. Right? Anything which is adders. No multipliers, no other circuits like that. Okay? Alrighty, let me kind of jot down some of the questions that you may have, and then we'll see where we go. Anything that you would like to see treated? Yes?
For dynamic power consumption,
Okay.
explain the equation E equals CL VDD.
Okay, dynamic power E equals CL VDD squared. Okay. All right. I'll see what I can do there. This is for generically or for inverters or? Okay. Why we come to that and why it's holding. Okay. Fine. All right. I can do that. Okay. Why no power when discharging? Yeah, that's an interesting question. Okay. How to derive a transmission gate from logic, right? From logic equation. Okay. Logic derivation. Okay. Yes.
Calculating the logical effort of carry-in of a mirror adder.
Oops, I have to get, okay, I'll have to calculating logical effort for the carry-in, right?
Yeah.
C-in of mirror adder. Okay. Yes. Sorry? Elmore delay. That's a good question. We have used it a number of times for pure change of resistant capacitors. And I would assume that that's something you should be able to handle. So if I have something like this, R1, C1, R2, C2, R3, C3, if I tell you what is the time constant of a network like this, you should be able to derive that. I'm not going to do anything more complex than that.
I'm not going to do that whole transistor 0 to 1 transition.
Well, this is a transistor 0 to 1 transition, right? If I basically put I replace the resistor by a transistor in a capacitor, so you can say, okay, what's the time constant of a network like this? This could be a set of transistors in a row with capacitors in between, right? Same thing. Approximately. Well, with some approximation. Yes?
Spring 02, midterm 2, problem 3B.
Okay. All right, so spring 02, midterm 2.
Yeah.
What problem is it?
3B.
3B. Okay. I'm going to have to look that up. This is not something that I have memorized, but we'll see what I can do on that one. Okay. It's good to be precise. Yes.
Logical effort for transmission gates.
Okay, logical effort,
I mean, how do you use the
yes,
initial inverter and logic?
for TGs. Okay.
The difference between linear carry select and square root carry select.
Okay. That's adders, linear versus square root carry select. Okay. Oh.
Tree adders.
Well, yeah, that's a little bit. I can go roughly through that, but obviously this is a pretty broad question. You can say, visual logic. I could do that too. And everyone's, I think it's a good list to start with, and probably other ones that come up. Let me kind of try to rank order them a little bit. Well, not rank ordering, but basically order them a bit. So, power. There's a couple of questions about power. Then there is the transmission gate logic, derivation, as well as logical effort. I see a question on the logical effort. There's some other questions. Logical effort of the mirror adder, as well as linear versus square root. Select. And three others, or what the concept is behind those. That's, I think, the list that I have here. I don't think, and then spring O2 midterm. Okay, cool. So let's start with that. You can either use the whiteboard. I think I can do that. That's probably easier. I can get some chalk. All right, let's get out of the way and start thinking about power. Okay, the first question is, why is energy equal to CVD squared? Okay. Take it in phase converter. Okay, and you can basically look at this as the supply is a supply that's basically connected between the two. Okay. So if you look, you assume that we have a sharp step here. Okay. We have an ideal step, which means that if we or we start, let's say, if you start first with a low and then you go to a high. In the first phase, we're going to turn on the PMOS device and instantaneously shut off the NMOS device. So they're never going to be on simultaneously. That's because we have an ideal step. And then in the second step, we basically raise the NMOS, turn off the PMOS, turn on the NMOS. So both of them are in different phases, or in different phases. They don't operate simultaneously. So let's look at phase number one. We start basically putting a 0 here. So we start with the down step. What we have is a capacitor which is discharged, okay, and a PMOS transistor which is going to charge it up, okay. So if you want to compute the amount of energy that I'm going to be taking, right? So you say, well, I'm going to take the overall energy, the power that's going to flow. The power, instantaneous power, is going to be equal to I VDD times VDD. That's equal to P. Okay? That's the power that I'm basically consuming, where it's a time variable because obviously this current is going to vary while we're charging the capacitor. Okay? The energy is the overall integral over the power over the period of interest. Let's assume that's infinity. We start with 0 and then we're going to charge up the capacitor. It's going to take, to get really to the final value, is we're going to asymptotically go to VDD. It's going to take infinity. So the energy is going to be the integral from 0 to infinity of VDD times I VDD dt. Okay? That's the way we get the energy. Okay? Now, some interesting things. So basically, if you say I VDD, this current here can be written down as CL times D V out dt. Right? The current basically that I'm going to charge, that we're going to flow here, is the current to charge up the capacitor. Okay? So this goes, so it means that the energy now is equal to 0 to infinity VDD times CL times dV out dt times dt. Drops out, so it's VDD CL times dV out. Now, by doing that, you're going to also change the integral, the limits here, which is going to go from 0, that's your initial value, to VDD. And if we solve this thing, we get basically equal to CL times VDD times dV out from 0 to VDD, that becomes VDD squared. Okay? So what's happening here is while we're charging, there's going to be a certain amount of current flowing to your supply, and the amount of energy I'm taking out of the supply is going to be equal to CL VDD squared. Okay? And now what's happening with that capacitance, with that energy, sorry, we figure out that in the end there's going to be some energy sitting on that capacitor. We've charged it up, so we have energy sitting there. And if you compute it, again, that's not that hard to do. The power, basically, again, you can, instead of using dVDD here, you put in here V out, and this becomes V out, and you find out that if you solve this particular equation, you see that the energy on the capacitor is going to be CL times VDD squared over 2. Okay? So it turns out that I take CL VDD squared out of the supply in terms of energy, and half of it is going to end up on this capacitor as basically charge. Okay? The other half was dissipated in the resistor or the transistor. It's a resistor basically. You have an electron going to basically while any current that goes to a resistor basically creates some heat dissipation. We turn that energy into heat. Okay? So next phase, that's where we are. So then we turn the inputs around, and I hope I have it. There we go. We turn the inputs around, and now we're just going to discharge. We disconnect the supply, and we turn on the NMOS. We have really a network that consists of a resistor and a capacitor connected to ground. That's what's happening in that phase. So we're going to discharge the capacitor, and what's going to happen is we're going to have current flowing through this resistor, which is going to dissipate the remaining energy. We take all the energy that we have left on the capacitor, CL VDD squared over 2, and just turn it into heat. And we're done. So that's why we say that actually all the energy is taken out of the supply when you charge. When you discharge, I just take what's sitting on the capacitor and I turn it into heat. Doesn't really take anything out of the supply. Now, in reality, this is a simplistic perspective. Why is it a simplistic perspective? In reality, it's not going to change very much overall, but if you think about it, if I again draw my inverter, and have my capacitor here, I always draw this capacitor capacitance to ground. In reality, it's not like that. Actually, we have some capacitance to supply voltage to the supply as well. Some of those, like for instance, if you think about this, the drain to source capacitance, or some of the capacitors we're sitting here on this node, the diffusion capacitance is actually of the PMOS, is actually a capacitor, or the diode capacitance, the junction capacitance is actually a capacitance to VDD, because the well where the PMOS device is basically set to VDD. So in reality, we have capacitance to ground and to VDD. It doesn't matter from the overall charge perspective. What basically happens is, you can see that in when we're charging this thing up, when this node goes up, we're discharging this capacitor. And when we're discharging this capacitor, we're charging this capacitor up. They go into either phase. But if you look at the same amount of energy that's basically going to be handled, the total amount is going to be exactly the same. It's going to be the sum of those two capacitors. They're going to be charged up either in the charge up phase or the discharge phase. So the simplification is perfectly fine. It doesn't change anything. But in reality, we're going to actually consume some charge. We're going to take some current out of the supply in both phases actually because of that. Okay? Yes?
So you said when you're charging the capacitor, did you say half gets burned by the PMOS, just like the
That's right.
resistance of the PMOS?
That's right. Independent of the value of that resistance. If it's 1 ohm or 1 teraohm, doesn't matter. It's always going to be CL VDD squared over 2. The resistor doesn't appear in there, interestingly enough. So there's an interesting question I could ask on the exam, but I'm not going to do it. Suppose what happens if I now asymptotically make that, so I can start with a huge capacitance, and I make it smaller and smaller and smaller. So suddenly I go to 0 resistance, an ideal switch. What's going to happen then with my energy? There's no resistance. It's an interesting question to think about. As I said, I'm not going to ask it on the exam, but it's a little thought thing, because if you cannot sleep at night, think about it. Okay? Good. So that's the power factor. Any further question on that? Now, obviously, this is the CL VDD squared is when you do a charge event, right? Every time I charge a big capacitor, I'm going to consume power, take power out of the supply. To get the real power dissipation, so now we have CL VDD squared. That's the typical energy that I'm going to take for every 0 to 1 transition. Now, to get the power, you have to multiply with how often it happens that I have a 0 to 1 transition. So multiply this with the frequency of f going 0 to 1. How often does it happen? Okay? Now, don't confuse this with the clock frequency, because depending upon your logic structure, not every gate is going to switch every clock cycle. Okay? It really depends upon the inputs that I apply and so on and so forth. So if I want to relate this to the clock frequency, we're going to have to take this f to 0 to 1 and translate it into f, where f is my actual clock frequency, multiplied with the probability that I have a 0 to 1 transition on a clock transition. So it's a kind of a ratioing factor. So maybe every 1,000 clock cycles I will have a 0 to 1 transition on the average. That's really what this probability is. So it's 1 out of 1,000 is basically going to create me power. And that's really going to give me my equation for my average power dissipation. Okay? So you have to be able to take a logic network and look a little bit. Obviously, as I mentioned in class about a couple lectures, actually, it's not even part of the, is it part? It's not part of the material of this exam. But if you have a complex logic network, I should be able to compute what the probabilities of a transition given the probabilities of the inputs and given the structure of the network. But remember, this can become very complex because of these dependencies. If you have reconvergent fan-out, you have basically sequential circuitry. Those probabilities are not dependent anymore, and the whole analysis of what's the probability a node's going to switch is very hard to deduce. So typically, like you did in the project, what we do is you simulate it. You apply the input vectors, and you look at all the nodes in the network and say, how often do they go back and forth? What's the average number of transitions per clock cycle? And if you have that, then you have the capacitance that can consume the dynamic power dissipation at that particular node. Okay? Is that clear? Good. So that's that. So let's talk a little bit about pass transistor logic. So how do we implement, suppose I have a certain logic equation. And actually I'm going to show an example in the exam that I'm going to go through in a minute. It's exactly going to do something like this. Suppose I say, I think the logic family, the logic equation I'm going to discuss is something like this. Plus CD. AB plus CD. Let's say, suppose that's the logic I would like to implement. F is equal to AB plus CD. So how would I do that? How would I go ahead and implement such a function? Okay? A couple of things to remember. If you have pass transistor, it's basically switch logic. And what do we know about switch logic is series connection of NMOS devices gives me an AND function. Parallel connection is an OR function. Okay? That's what you always have to remember. That's step number one. So Composition rules, a plus is parallel, and an AND is series connection. What's the second rule? Pass transistor logic, unless we're making it dynamic, which I'm not going to do, it has to be static. We assume it's static logic. And static logic, per definition, you said something has to be static. It means that under every input pattern, whatever the input pattern is, in a standby mode or in a steady state mode, we should always have a low resistance connection to either VDD or to ground. Okay? It has to be low impedance. The output node always has to be low impedance. We don't want to have a high impedance capacitive node. Now, let's look at the example, for instance, of an AND function. If I just say, well, I'm going to implement a function which does A and B. Let's say I do A and I connect B to that. Right? That's a nice AND function from my perspective. This A and B, the output is going to be high here when A is high and B is high. Okay? So that looks good. But we have a problem here is that if B is low, this node is floating. It's undefined. So the zeros in this case, or the B, if you look at the complete truth table, 0, 0, 0, 1, 1, 0, 1, 1, A, B, and we want to implement an AND, 0, 0, 0, 1, it's only under this condition, and actually also when this condition is true. In both those conditions, we have the output well defined. Because B is high, means that this transistor connects, and it basically just connects A through, which either 0 or 1. So we have a well-defined output state. In both of the other cases, we don't really know. It's floating, which means that it might remember, because this is a capacitor, it has memory, it might just remember a previous value. Sorry, and if I don't condition it correctly, this thing is going to be wrong. Okay? So we have to do something, add some stuff to it in such a way that we are sure that the other ones are also defined. It's the cases where B is equal to low. So what you always do in passive transistor logic, you always have two parallel branches. One of them going to be defined by B, the other one defined by B bar. In this case, we know we're covering all the different rows of our truth table. So we already know this side is A, that's AB, that's fine. So what else do we have to implement? Well, we have to make sure that B0 is high, or B bar is high, or B is 0. We have to make sure that this node is 0. I have a couple of options. I just can connect this to ground. Yep. If I connect this to ground, I get a 0, bingo, I'm fine. Because the output is 0, bingo. The other thing I could do, if I really want to, because I know at B0, B bar is equal to high, then B is equal to low, I just can connect B here. Same thing. It doesn't really matter. You can do both, give you the same result. Okay? So that's one option. Now I can do the same thing for OR functionality. I look at my truth table. Let's do a very simple case. Let's do this quickly. I'm going to make an OR. I'm going to change things too much. So let's put down the truth table here. Our function is 0, 1, 1, 1. Okay, so let's look at the case when B is equal to 1. In that case, we see that the output is also going to be 1. Right? That's what you expect. So B equal to 1, I could do that. Or I could connect it to VDD. One of the two, both of them are fine. The other one, when B is equal to low, we see that the output is equal to A. Right, if B is low, this is equal to each other, this is equal to each other, I just connect A here. We're done. We have basically covered again our 4 rows of our truth table. Okay? Now, so step 1, I'm here, I have AB plus CD. I want to make it a little bit more complex. So I showed you how to do, there's now a couple of ways of doing this thing, but the simplest way of doing this is composing complex logic by putting elementary logic together. So I'm going to compose this out of 2 input gates, and have two input gates in series of each other. So remember A and B, that was something like this. So we have B and we have B bar. We connect A here and we have, what is this thing here? That was B. Okay. Same thing with C and D. Independent what you pick. C and D, so let me pick D here. That's D bar. This is C and this is D. So now I've implemented A and B and C and D. And now I'm going to take the same circuit I have over there. So okay, I'm going to take now the first input of my circuit here. Let's assume that I'm going to take, this is now X and Y. Let's call it that way. Let's use Y as a control signal. Now, here's a little challenge. Okay, so what I've done so far is that I have now created X and Y. You can see that you need here signal and signal invert. That's why we have differential logic. Okay, so when I implement X, it would be a good idea to also implement X bar and Y bar, which is NAND and NOR. And again, I can look at my truth table and figure out how to implement the NAND and how to implement the NOR. Actually, all of those are very nicely enumerated in the text. The circuits and how to connect them together. If you look at the text, we have a nice little table in there that does all those things. So I need also X and Y. So I have X and Y. I also create circuitry that does X bar and Y bar. And then I basically connect those things. I take X and Y. Now instead of A, I'm going to make this X. This is Y. This is Y. And this is Y bar. And that's my function F. So I take 4 elements here. Let's say I add one more thing here. This is going to be the same deal. B and B bar. We know that. And then you have to figure out how to connect A here to get X bar. You have C, D bar, and you figure out how to connect C and D to connect Y bar. And then you connect this to this, and we're basically done. So what I've done here is actually implement my complex logic function as stages of 2 input logical gates. Okay? But remember, there's the challenge of threshold losses. Right? So if I start doing this and I start complex things, I have a VT loss here. Now if I use X, or if I use Y, which is equal to VDD minus VT here, I get VDD minus 2 VT here. Okay? How basically do I avoid that? Well, the trick is to put in sometimes buffers or inverting buffers behind that and basically reinstate your logic. In this way, you don't have that problem. You basically don't have the VT drops. This is what complementary passive transistor logic does. You have a bunch of blocks like this, and you keep on stacking them together, and you can basically create arbitrary logic families. Okay? So think about it, simplified way. There's other ways of doing this, by the way. You can make passive transistor logic in a number of different ways. If I really want to be clever, I can throw some PMOSes in a network, what people do. But then it gets a lot more complex. So think about it. You have your basic logic function, AND, OR, XOR, basically. These are the basic things we're going to use. 2 input logic gates. We're always going to create signal and signal invert. So we make it differential. And then we stack them on top of each other, or in series of each other. And this way I can implement any logic function you can imagine. So that's the way, as I said somewhere in the exam that I'm going to discuss in a minute, we want to implement this. The question is, implement this thing as complementary logic family. It's using CPL. That's really what you would do. Okay? Now, there was a second question about the logical effort of passive transistor logic. And it's a little bit trickier, but let's go to that. It's not as easy as CMOS. But let's think about it. So assume that I have an AND function implemented in CPL. I have an inverter here. That's B, B bar, A. Let's put it to ground because that doesn't change. The nice thing about putting it to ground instead of to B is obviously is that when I put a B input there, I load the previous stage. When I connect it to ground, there's no load on the thing in front of here. So from a logical effort, that's probably a better idea. Not using B or B bar as a connector, but basically connected to ground or to VDD. Okay. So remember the definition of logical effort. What I want to do is figure out for every one of the inputs to the output, right, what is the amount of equivalent capacitance that I see at the input for the same driving strength as an inverter? Okay, that's always what you have to think about in terms of logical effort. Now, the challenge here is that it's very hard for me at this point in time to define this driving strength. Because what does that mean? A is kind of a thing sitting in here, but what is A? Well, A is also itself generated by a previous stage, and it's very hard to discuss the driving or the logical effort of a pass transistor logic family without basically figuring out how A and B is basically generated, because they're part of the basically network, of the driving strength of the network. So in case of A, since always we have, let's say, an inverter in front of us, we have to add the inverter here. Yes. If it's not an inverter, you have to basically chain it all the way back. Suppose I do chains of pass transistors. I have one more and then another one, another one. You have to look all the way back to the VDD or to the ground connection, because you have to look at the whole series chain of resistors, because that's going to determine your driving strength of your device. Okay? So this is the simplest case, right? I have an inverter, pass transistor, inverter. But you could indeed have more complex networks where you have two pass transistors in a row, which we would very often actually do. But let's assume for now that we have an inverter here. I know, let's assume that I'm going to make all those devices 2 to 1. Same thing here, 2 to 1. So what is the driving strength? Well, let's look at there's a couple of inputs I would like to study. Let's look at A. Well, actually, in this case, it's going to be now becoming A bar, because A is not a primary input to this network anymore. And we have B. Let's look at B. What's the logical? Well, let's assume that it all depends on how you size the device. Again, this is 2 to 1. If I would like to size it similar to an NMOS, okay? And here's a little assumption. It's not really similar. I have to make this thing size 2 as well. Right? If I take basically look at the charging network here, let's just think about for a second how I would size this. Okay, I want to make sure that this network here, this resistor, is equivalent to the charging resistance of an inverter, right? Minimum size inverter. That's the definition of logical effort. So how would I have to size it? Well, I have 2 transistors in series here, 2 NMOS devices. 2 devices in series, I'm going to have to double them up. This is equivalent to a single NMOS device, right? The same thing, this similar NMOS, this has a resistance of an NMOS of unit size 1. So I'm going to make this size 2. Okay? Now, if you look at the total load I see on B in this case here is 2. Right? If you look in this thing, it's basically it sees one single NMOS device with a load of 2. So capacitance for the same driving strength, in this case that B sees is 2. Well, for an inverter we have 3. Minimum size inverter. So logical effort is 2 over 3. Okay? Let's now look at the case of A bar. As I said, A is now a derived signal. Let's look at A bar. Again, we size the devices, make it 2, so it's still basically 2, same driving strength. We keep the same driving, basically sizing of the transistors. What does A bar see here as capacitance? 3. So in that case, your logical effort is going to be 3 over 3. Is 1. The same as an inverter. And that's exactly what you really see, right? You see the A bar only sees a single inverter, and its drive strength to charge up this capacitor here is equal to the same thing as a single NMOS device. Yes?
How's that equal to a transistor? You said the driving strength is the same as a transistor.
It's an inverter, right? Well, if you look at the resistance here, is I have, oh, wait a second, maybe, since we have two in a row. No, actually, you're right. Obviously, I have to double this up. And in that case, 4/2, so sorry for that. So this has to be 4. This is 2 plus 2 is actually, it's 4 in this case, and it's 4/3. 1 second here. No, it's 3. So this is 4/3. That's exactly right. Because that's, no, 1 second. Let me just make sure I'm not confused here. 4/2, yes. For this thing, it's 2/3. That doesn't change. This thing sees 6/3 is equal to 2. Correct? So what I did here is, because you have a series connection, I had to double the devices. So that means my inverter here has to be sized up to 4/2. Okay? So what that means is that the capacity I see here, total capacity is 6. The drive compared to an inverter where you see only 3. It's double the size. Right? For this case, however, is the capacity I see here is only 2. So you get 2/3. So the logical effort from the gate inputs, the ones that go to the gates, is substantially lower than the ones that basically connect to the sources or the drains of the transistors. Right?
So the value 2/3 is the logical effort
Of B. And 6/3, 2, that's the logical effort of A bar. Okay? So this is LEB. Now, LEB bar will be exactly the same. Right? It's symmetrical. For A, well, obviously there's no A in this particular circuit, but you have the differential circuit. You will see that A basically will appear there, and then you have to do the same type of thing. But you're right. So that was good. 2/3 and 2. So that is a factor of 2 difference in logical effort depending what inputs I basically pick, which is very important. It's an asymmetrical situation. Okay? What's that? Good. My math is, it's late in the evening. Okay, is that clear? Good. So next question was logical effort of the mirror adder. Now I'll try to see if I can bring that up the screen and show it on the diagram, because for me to draw the mirror adder would be some of a trick. Let me just go here. Lectures. And I hope I have this magical little connector. Now let's see if magic happens. It doesn't very often. Did you get the signal? Macs are beautiful computers, but I haven't figured out how to do multiple displays very well. Let me try to do this. Okay. Displays. Yeah. Magic. All right. Okay, let me try to find a mirror adder here somewhere. Okay, here we go. Oops, it should be reversed, but that's okay. It switched my do displays, but still trying to figure this thing out. As I said, we should basically ask Mr. Jobs how to figure out how to drive multiple displays well. Anyhow, so mirror adder, and what we're looking for is how to size the carry in versus carry out path. Okay, and what the logical effort is for the carry in. So there's a couple of things you should be aware of, and let me do the previous slide here. So here's your mirror structure. We have the first stage of the mirror. This is the carry in to carry out. Okay, and I assume here that I use this inverting logic strategy, that I don't need an inverter in between. So this is the inverting carry idea. So let's look at the carry in, and this is that's the mirror adder structure. This is a sum. The sum basically just acts as a load, and since it's not critical, I assume we're going to make it minimum size, and we're just going to size it for identical drive strength. So the sizing of this thing is 2, 2, 2, 2, 4, 4, 4, 4. Okay. So then we have the other structure here. We basically size up. This is another load factor. So if you look at the carry in, it goes basically the carry in, the carry out is connected to this device. It connects to the carry in of the next stage, and is also used to drive some of the carry in of the sum stage of the next type of adder bit. So we see that this node here has quite a lot of fan out. Right here, plus CCI of the next stage. Okay, so let's look at the logical effort of the carry in. Okay, again, what we would like to do is create. You want to create a. You look at this structure here. It says what's the overall input capacitance that this thing basically sees. Okay, and so we look at here. This is. The carry gate has a logical effort. Well, it's an AND gate. It's a very straightforward type of structure. Logical effort of this thing is going to be approximately 2. Right? If you look at what this thing connects into, the carry, at least if you look at this particular gate here, yes.
What about the carry-ins on the sum?
This one's here.
To the far right.
This one.
6, 6,
This one here.
3, 3, 3.
Yeah.
Don't those have carry-ins also?
No, there's no carry-ins in here. The carry-ins actually happen here. I don't think there's carry-ins on those. No, they actually do, but there's a carry-in of the previous stage. You see it happening here. So this is CCI of the previous stage connects to the carry-ins right here.
Yeah.
Okay.
For the top adder, the top full adder.
This is going to be connected to the previous one. Right, if you look at this input here, this is connected to the previous bit. Or if it's the first bit, it's going to be connected to ground.
Is it connected to the same CI as the one on the left?
No. No, you can see it, right? So we showed 2 bits here. CCI of this bit, so you get C out of this thing. C out of this bit connects to the carry in of the carry stage of the next one. It connects to this gate, and it connects to this gate. Oh, you don't see the pointer? Oh. I'm sitting on a different screen. That's the problem. Okay, let me go here. So you see the carry in. Sorry for that. So the carry in of here, this is the carry out of this stage. connects to the carry in of this and of the next stage, plus 2 places in the sum generation. Right here, those 2 transistors, and right here. But that's just your logical connection. Right? So why is this going to be important? Well, obviously, I would like to figure out how to size those gates. But the question really was, what's the logical effort of this gate? That was the first question. What's the logical effort of this gate? Well, we know that, right? It's a NAND. It's basically it's actually almost it's a NAND gate. So the sizes of these devices, if you would basically size this for unit driving strength, right? The same strength as an inverter. This is going to be 2. Oh, back in the same thing. I should basically be looking here. This is 2. This is 2, this is 2, this is 4, this is 4, this is 4. So you get 6 as a total capacity I see here. 6 over 3, I have a logical effort of 2 for this particular gate. And that's the one I'm mostly worried about. Because that's the one, if you look at the carry path, what I have was one gate driving a load capacitance for the next. That's your carry path. Right? That's what I'm trying to optimize.
Can you draw like a box around one full ladder?
Yes, right here. No, right there. I lost my pointer again. I should have brought my other computer. It's nicer to have a tablet. You see this box here? This is one full ladder. This is your carry generation. So carry in to carry out. This is a sum generation. That's what the mirror. Let me, if we just go, I'll show. Here it is. So here's your mirror adder, right? So this is one stage. You get your carry in, carry out bar, going to the next stage. And then the sum generation basically takes a couple of inputs. It takes A, B, the carry in of the previous stage, plus obviously the carry out of this stage as well. So it's A, B, CO bar, and CI as the input really. So you have 4 inputs into the sum logic. But as I say, I'm not too worried about this. This thing only acts as a load on this node here. That's the only thing I care about. Right? So if you go to the next one, next picture here, I just draw 2 of those. The same thing, but I repeat it 2 times. Okay? So as I said, the load, the real thing I worry about from stage to stage, the delay, is the one that goes like this, right? It goes to here, goes to here, goes to the next bit, goes to the next bit. That's my carry path, right? That's the one I'm trying to optimize. The sum stages only act as a load. And obviously, we're going to have to size it correctly, but we can figure out what the load is by minimum sizing this and designing the device. For instance, here, I get a load of 6. This here is 3 transistors in series. So I have to triple up my devices. That's a capacitance of 9. That's another capacitance of 6. And here we don't know exactly what the capacitance is going to be. It depends upon the sizing factor. So C load on this node here is going to be 6 plus 9 plus the input capacitance CCI, which is the same as this capacitance, right? They see the same thing. They're the same cells. So my load capacitance is CCI plus 6 plus 6 plus 9. And we also know that C load, and so that's my equation here. C load is CCI plus 12 is plus 21. Okay? Now, I want to know, so we know that the logical effort of this guy is equal to 2. We want to make the stage effort equal to 4. Okay? So what should the fan out be? Well, the logical effort, the stage effort is equal to the logical effort times the fan out. We know that we want to get a stage effort of 4. That's a good number, the magic number. 4, we know that logical effort is 2. It means that the fan out, that the optimal fan out of this node should be equal to 2. Okay? So that's the fan out. Or the ratio of this capacitance, well, I'm back again on the wrong picture here. The ratio of this capacitance to this capacitance should be equal to 2. Total capacitance of this node should be twice the capacitance here. Or in other words, C load should be equal to 2C times CCI. I eliminate this here and I find out that CCI should be equal to 12, 21. And I basically, as a result of that, I figured out what the size of my transistor should be. Okay? Based on this, Now I can size my devices. You see 7 plus 7, 7. This one I make double the size, 14. The load capacity I see here is 21. Bingo, we're done. So this is optimized for performance. So logical effort is 2. That's easy to derive. That was the original question. But the real sizing question is a little more complicated. I said I want to basically get the optimal sizing in such a way that I get minimum delay, which means fan out of 4. We know logical effort 2. We know as a result, stage effort is equal to 4. Logical effort is 2. Fan out is equal to 2. And we know what the capacitors are. The only thing we're missing in this equation was CCI. We fill it all in, and we find our result of that. Okay? So it's a fairly straightforward realization of logical effort, stage effort for a multi-stage type of thing. There's not even a branching thing I have to worry about. Yes?
Well, when you have a multi-stage, I don't see how there's any way to not have CI at the carry-out stage connected to the CI at the sum stage. Won't they always be connected? Because if you have a full adder block, there's only one CI input, right?
That's right.
So no matter what you hook up to that, it's going to see both from the sum and from the
That is correct. I didn't say that. Right? So that's exactly right. If you look at the load here, you see here's your cell. Right? CI goes to CO bar. CO bar goes to the next stage. And in the next stage you will connect, and the next stage will be called CI, obviously. So it's going to connect to here. It's going to connect to here. Well, once again in the wrong place. It's kind of hard to have two different screens. Here, 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 and there. That's where we're going to connect it to. Plus, obviously, also in the input of the next carrier stage as well.
So the C gate of CI would be 4 plus 2 plus 6.
No. If you look at, I'm worried about, I'm looking at the logical effort of this gate. Okay? I'm not looking at, logical effort is typically defined as a function of a particular gate. Right? I'm trying to figure out, here's this gate. What's logical effort of this thing? What logical effort is 2? I know that. We can define logical effort of this stage as well. It depends on basically what transistor you look at, but it's probably going to be 2 as well. This guy has a larger logical effort because you have 3 transistors in series. So you know that. So this is per gate. I'm not looking, you cannot say what's the logical effort of a mirror adder. You have to look at the individual gates, and then you say the logical effort of a path is going to be the multiplication of the individual logical efforts. Right? You have the path logical effort is the product of the logical effort. So if I want to say, what's the path logical effort of a ripple adder that has 24 bits? Well, I find the logical effort of an individual carry stage, carry in to carry out. I figured that out. And then every one of those adder bits is going to basically multiply this out. So I'm going to get 24 times the logical effort of an individual carry stage. And that's going to be my path logical effort of the complete ripple adder. Okay? Seems like still some puzzled faces. This is a very good example, I think, to work through, because it really works. It shows how, for at least for combinational logic, how we can basically use logical effort to size things very nicely and come up with very clean answers. Okay? Is that clear? Okay. Good. So there was 2 more questions about adders. And the first one is linear versus square root carry select. Okay? So the idea of carry select is the following. You're trying to get around the problem of having a adder delay being linear in the number of bits because of the carry propagation. Every time you have propagation, you have 100 bits, so you have to go to that carry pod 100 times. So I said, well, if I can take it into individual blocks, and I divide my adder into chunks, maybe of 4 bits or 6 bits. So again, it's going to be interesting to see what the optimal number is, but I can almost imagine it's going to be 4. If you would basically divide it optimally, you will see that you're probably going to have 4 stages. But anyhow, so what carry select says is the following thing. I have a block of 4 bits. Right. And so you divide my adder into those blocks, 4 bits. The problem with block number 2, block number 1, I can start computing right away because I know what this input carry is. It's going to be 0, right? Block number 2, I cannot start computing the carry till I know what the carry output of the first block is. Right? That's the problem. You have to wait, and that's why you get your delay. So the idea of carry select says, well, you know, what I'm going to do is, I don't know what the answer is, so I'm going to compute both. Right? I'm going to assume that it could be 0 or it could be 1. So I'm going to have 2 carry paths. So I apply my inputs here, A, B, propagate, generate, or whatever you want to do. And one I'm going to assume is equal to 0. The other one I'm going to connect to 1. And I compute the carry output. Given the inputs, because the inputs you have available, you can start computing this right away. So a number of clock, or basically a number of clock, not clock cycles, but a certain delay later, I'm going to have both answers here. The carry output of this block, assuming that the input is 0, and the output carry output, assuming that the input is 1. Okay? Now, then I say, okay, now what I could do is put a multiplexer here, take both in, and once I know the output carry of this thing, I can just say, I'm going to select the top one or the bottom one. Because if it is a 0, I'm going to select this one. If it's a 1, I'm going to select this one. Okay? And the same thing you do with the next one, and so on and so forth. Okay? So I hope by doing so that I can basically avoid that very long chain and maybe get around to linear dependency. But in reality, you don't get around to linear dependency, because you look at, if this would be 1,000 bits, I'm still going to have to go to 1,000 divided by 4 is 250 multiplexers. It's n divided by 4. If by every block has 4 bits, I'm going to have 250 blocks. So I'm going to have to go to 250. My critical path is going to go to the first stage, and then multiplexer, 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 in the worst case. So I have 250 multiplexers I have to go through, which is still linear in n. It's proportional to n over 4. But it's still proportional to n. So if I double the size of my adder to 2,000 bits, I'm going to double the delay. The only thing I gain now is that it's n over 4. It's not n anymore. So what I have done is kind of change the slope of this a little bit. Okay? So that's so far what a linear carry select does. It's a good thing to do, right? Because I change the slope for long adders, I'm going to win. But it's not dramatic. I would like to get around that linear dependency. And what you do here is the following one. It's a very simple trick. It has to do with basically looking at critical paths through your logic. And I say, well, gee, if I look at my critical path here, what's the problem, right? So I start computing my block 1. I get the output of this block 1, and then I feed it in here, goes the multiplexer, and I go to the next one, and so on and so forth. Now, if I look at this multiplexer, let's say, and I look at a time tx or tc, my carry arrives, but the arrival times of tc equal to 0 and tc equal to 1, this signals here, the further you go down the chain, this takes basically, you put the inputs in here, you go to 4 stages, bingo, you have those results. Right? So for every block, all those carries are sitting there, waiting, till the carry arrives. In the beginning, it's going to be about approximately the same block. Here, it's going to be approximately the same time. But the further you go down the chain, you will see that all those carries are going to be sitting there, and they're going to have to wait for the basically input bit to arrive. And here's where the clever tricks come. Say, well, since these things are not doing anything, why not make this block a little bit bigger? Instead of 4 bits, use 5 bits here. This 5 bits is going to basically delay the arrival time, but that's okay because this guy is not there anyhow. So what you're going to make sure is that those signals and those signals arrive at the same time. Which means that if you go to the carry select block, you make your blocks gradually bigger and bigger and bigger and bigger. Okay? So you start with 4 bits, 5 bits, 6 bits, 7 bits, 8 bits, and so on and so forth. Now, why does this now get around the linearity problem? Well, it's quite simple. If you now figure out how many blocks I need for the complete adder, it's going to be dramatically reduced. Because I make block bigger and bigger blocks, I'm going to need less blocks. So the number of multiplexers I'm going to have in my critical path is being reduced, which means I have a net gain. And if you do the analysis, theoretical analysis, you see that actually becomes almost like a square root. Okay? So I'm starting to get a square root dependency. And that's quite beautiful because this is linear. Square root goes like that. It saturates out. So if I go to a 1000-bit carrier select adder or a 2000-bit carrier select adder, the difference in delay is almost nothing. It's almost the same. So those things really pay very nicely for very long adders. Don't do this for 4 bits or 8 bits or something like that. It has to be at least 32 bits. And then you're going to start gaining. Carrier select adders, as we'll see in one of the next following lectures, are, for instance, very popular in the last stage of a multiplier. We show how you basically get around, but in the end, you need a fast adder. That's why this logarithmic carrier select adders are actually quite popular. Okay? Clear? So that's the select. We can do similar things for the bypass. Bypass is the same idea, right? What I'm going to do with the bypass is it's a little bit different. I'm not going to compute both, but I'm going to compute the precondition. So you have, again, you divide your adder into blocks. Now, when is a carry from block 1? This is not a single bit. This is a block. Block 0, block 1, block 2. When will the carry from here propagate to the output? Because that's the longest path. That's the critical path. Is when the input carry has to go all the way from bit 0 to bit 100 or bit 1000 or whatever it is. That's critical. Well, in order for this to propagate from here to there, I need the condition that all these bits are in propagate condition. So we call it the block propagate. So B1 is equal to P0, P1, P2, P3 of the different bits that go into this block. So if all of them are in propagate condition, we know that an input carry is going to zoom right away to the output. So rather having done that, we say, okay, when we know, we're going to feed them both. When we know this comes in here, when we know we're in propagate, we can select. When we're in propagate condition, we do PB1. We know it's propagate. I'm going to create a bypass. I'm going to skip this whole block and feed the carry right away into the next block. Because we know we can do that because all our propagate bits are 1. If one of them is 0, then obviously my carry, I'm going to break this path, and I'm going to get my carry coming out of this guy, which is going to originate somewhere. But it's going to originate here because if we know it's not all in propagate, so there has to be a generator or kill somewhere in here. So somewhere you break the path in this block. But the longest delay is going to be 1, 2, 3, 4 bits, bingo, get out. So again, this is still linear if I make all the blocks the same size. But, and actually it's an interesting exercise, you actually figure out you can also make this square root. But it's not making your blocks longer and longer and longer and longer. Now what you do is, you start with the first block, which is small, you make the next one a little bit larger, make the next one a little bit larger, make the next one a little bit larger, and then in the middle, you start reducing the size again. So a carrier bypass with square root dependency is going to look like this. You make your small blocks, larger and larger, large blocks. In the middle is the largest block, and then you make them smaller again. And the main reason for that is that the last stage, the sum output has to basically go to this whole stage. If that would be a very long one, you get penalized. So that's the main difference between the carrier select and the carrier bypass. So remember that. It works nicely as well. It's just not just as effective as carrier select. Okay? Now there was a question about 3 adders. Now that's obviously a long question. I can basically talk about half an hour about this. I'm going to make it quite short. 3 adders are based on the following concept. What it really says is the following thing. If I look at, let's say, a propagate. Propagate, or the carry out. The carry out of a block is going to be equal to a generate at a certain stage. Let's call this I. Or a propagate in stage I times the carry of the previous stage. Let's call this carry I minus 1. We call this carry I. This is the basic equation. It says you have an output carry when the input carry is 1 and you have a propagate or when you have a generate, right? Very simple equation. Now I can write the same thing for Ci plus 1 is equal to Gi plus 1 plus Pi plus 1 Ci. Now I know Ci, I can take this equation and fold it in here. So it's really equal to Gi plus 1 plus Gi plus Pi plus 1 times Gi plus Pi times Ci minus 1. Okay? Now I can keep on doing this. I can replace Ci minus 1 by Ci minus 2, and so on and so forth. I can keep on nesting the same equation, and in the end I get one single logical expression of the carry out in the function of the first carry in of my adder. So C0. I can do this for 32 bits. I can write one very, very long nested equation. Now obviously you know that nesting equations say, well, I implement this as a single logic gate. And that's fair, but it's kind of problematic because you know that if I keep on increasing the fan-in over logic gate, the delay is going to go up quadratically. So you don't win, actually, you make something actually which is going to be slower. So the key observation that basically resides in tree adder says, okay, I can take this equation, but what I should do is not kind of keep on nesting them. What I can do is reorganize them a little bit. I'm going to use the associativity, property of the generation. And it says the following thing, is that if I take, let's say, a number of bits, I have 2 bits, let's say. I'm going to combine them, bit 0, bit 1. I have the propagate conditions for those. I can generate what's called a propagate condition for the total block, like we did before. The block propagate, which is going to be equal to P0, P1, right? We can do that. We can do the same thing for bit 2 and 3, P2, P3. And for bit 4 and 5. Basically, the block propagate is going to be P4, P5, right? So rather than basically nesting them, I'm going to compute all of them. I'm going to divide it into blocks, and I'm going to compute the block propagate for each block. Now, what we know also is that now, if I combine those 2 together with the same function, it's an AND function, I can find P0, P1, P2, P3. Okay? And so on and so forth. I can start combining things kind of all in parallel rather than having to wait for the things. And in the end, I basically have one block propagate which constructed all of those type of things. Now you can see that if I, let's say, do this with 2, the number of logic stages I'm going to have here to compute this whole thing is going to be log 2 of the number of bits. So the beautiful thing of a tree adder is that I take a linear equation, something which is a long expression of basically staggered thing, something that basically does something like this. Let's make it very simple. This connects to this, connects to this, connects to this, connects to this. Now I'm saying I'm going to compute this like this. 2, 2, I combine this, so you have 2 more. I combine this, and I combine this, and I combine that. And I connect it as a tree. And the number of stages in this tree is going to be log 2n of the number of bits I have in my structure. And that's why tree adders are always going to be logarithmic. Now, there's a variety of ways of combining these things together. Okay, I can use 2 bits at a time. I can use 4 bits. That's what's called the radix. I have radix 2, radix 4. And there's different ways of how I combine the different intermediate results together. If I generate them all, or I kind of first generate only the output one, and then I kind of derive the intermediate one later on. It's a question of density. How many interconnections do I have? What's the fan out in the intermediate nodes? But all of them are basic derivatives of the same thing. Okay? But the beauty of it is this logarithmic dependency. Logarithmic, if you look at it again, you plot log 2 or log 4 as a function of n is going to be better than square root out of n. So in principle, this is cheaper, or not faster, than a carrot select adder, but it's going to be more expensive. Because you see this whole tree, you do a lot of extra things, which I don't need in a ripple adder. The ripple adder is the cheapest adder I can come up with. It's the simplest hardware. This has redundancy built into it. Okay? So that's kind of in a nutshell what you should know about adders, 3 adders. But I said you kind of read through it in the book, and it explains it fairly carefully. Okay? All right, so we have about 15 minutes left. Let me first go briefly to this exam of 2002, and then I'll see if I can get to Spring 02 Midterm 2 question 3b. Okay? Let's see where we can get on that. So let me just kind of go to the question, because I picked this one because, as I said, they're quite relevant to what we had. There's my mouse here. I'm trying to make sense of what this computer is doing to me. Okay. Okay. So question 1 is the one I kind of referred to before. Question 1 will say, take a logic function f equal ab plus cd. Part 1 is implement this in complementary CMOS. Fairly straightforward, but you have to be aware that complementary CMOS is inverting. So I'm going to need 2 stages to implement this thing. So complementary CMOS implementation of that, that's a giveaway. It should be fairly easy to do that. AB CD and then I have to find the PMOS equivalent, so you get A in parallel with B, and you have C in parallel with D. A, B, C, D. Now this gives me F bar, so I have to add an inverter to it to get my AB plus CD. And there's no way with complementary CMOS I can implement this function in one shot, because it's a non-inverting function. Okay, so that's that. Part 2 is implemented in domino CMOS logic. So same function, what should I do? Well, domino is absolutely in midterm. Domino is in dynamic logic, right? Dynamic logic. Everything is in dynamic logic. Up to the last thing is NP CMOS. The last stage is basically where we do cascading. You go to domino logic, and the last stage, the last slide I think, which is included, is the NP CMOS slide. Okay, domino. Now domino is quite easy. What I have to do is the same thing. Domino has the advantage that it is a non-inverting logic style. It's always non-inverting because you have that extra inverter there always present to you. So you have your clock and MOS. This thing becomes simpler. This is just your pre-charge device, PMOS, connect to the clock. This goes to the inverter. That's my function F. We're done. The inversion basically comes in there for free because domino is always having an inverter. Okay? Number 3 is implement this thing using differential domino dynamic logic. Okay? So differential logic. Nice thing about differential logic is that now I have basically a couple of things. I can do this with a single stage. If it's not domino, suppose I want to do just differential dynamic. Okay? We know we have always single and single invert available. With differential, we're going to have to build a second stage, which has the, this is AB plus CD. If I want to take the inversion of this, remember differential logic, you have a pull-down block and you have the complementary pull-down block. Both of them implementing complementary functions. So I have to implement a function which does, this does AB plus CD invert. Now I have to have something that basically does this, right? 2 inverts. I take this becomes A bar plus B bar and C bar plus D bar. Invert, right? So by second block would be A bar plus B bar. So I'm going to put this two in parallel. And I put here A bar, here I put B bar. Same bottom level transistor. C bar, D bar. And connect all those things together. No, not connect them together. So this is going to be, you pre-charge this. I pre-charge this guy. This is going to be F bar. This is going to be F. We're done. That's all you need in this particular case. So I really have my complementary network. I know I have A bar, B bar, C bar, D bar, so I can implement this thing, so I don't need that extra inverter in this particular case. Okay? That clear? So the nice thing about it is I save out that inverter. Okay? And that's why complementary or differential logic sometimes has some advantages in terms of performance. And the last one is really the pass transistor question. Implement this in differential pass transistor logic. I already showed that. Right? You basically make AB, you make CD, and then you combine the two together into an OR function. Bingo, you're done. Okay? And that's question number 1. So let's have a look at part number 2. It's a logical effort question. Let me just get this thing here. That's the wrong mouse. Wouldn't do very good for me. So, here you have a domino inverter. CLK, CLK, PMOS, inverter A, F. So we have and have an inversion. Okay. So the question is really as what's the logical effort of this particular gate? Actually, we have done this. Assume now that we're going to size our inverter. It really depends a little bit about the sizing of the inverter. What's going to happen here in terms of logical effort of the next stage. Suppose I make this thing 4-to-1. Okay? Suppose I skew this. Remember when I have the in a domino inverter, the second inverter, it's a good idea to move the threshold upwards, because the only transition that I will see here during evaluation is a downwards transition. So actually skewing your inverter is a good idea. Okay? So we're going to make the PMOS double the strength of the NMOS, 4-to-1. Okay? Which is going to implement or going to impact its logical effort, obviously. Okay? We'll come back to that in a minute. So let's look at the logical effort of transistor A, of the first stage. This is now a 2-stage block. So we're going to have to actually combine the logical efforts of the 2 stages together to get the total pad logical effort from here to here. Okay? So what's the logical effort of this inverter? What should I do? So what's the size of this device? 2, right? 2. So what I see here, the signal driving strength as an inverter, at least in a pull-down network. So I get 2, and the inverter has 3. So logical effort of this first stage is going to be 2/3. Correct? Okay. Now what's the logical effort? If this would be a normal inverter, 2-to-1, I would have a logical effort of 1. Right? But here the situation is a little bit different, because we have sized this device, we skewed the threshold upwards. And the main reason again for that is, remember, you pre-charge, this is a pre-charged node, and during either going to stay high in evaluation or going to go low. Discharge. That's the only thing that can happen during evaluate. You pre-charge and you stay pre-charged, or you're going to discharge your node. So it's a good idea for my inverter to start working as soon as possible. The sooner the better. Right? That basically is going to reduce the propagation delay of this particular node. That's why we move the threshold of this inverter upwards. Okay? And we can do that because we're never going to see a opposite direction except during pre-charge. But we're not worried about pre-charge. That's not my delay that I'm really worried about. So that's why we skew this inverter. Really move the threshold, the switching threshold of this inverter upwards. So let's think about the driving strength of an equivalent inverter. Well, for an equivalent inverter, if you would have to do that, let's look at that. So you have now a device here, CMOS inverter, where this is 1. So during evaluation, so this is high, we're going to pull up, this is low initially, so the transition is we're going to basically pull up this thing to VDD. We're going to charge this thing upwards here. So what you notice is that this has more driving strength than a minimum size inverter, right? It's actually 4 to 1. So actually, if you would have an equivalent inverter, it would be something like 2 and 1/2. Right? If I would size them up equally in terms of driving strength. This has the same, from a pull-up perspective, has the same driving strength as this. So my capacitance I see here is actually 2.5. Okay, to make the same driving strength as a normal inverter, I have 2.5 over 3. So you see that this inverter here is actually faster than a normal inverter. Okay, 2.5 over 3, or basically is 5 over 6. So my total logical effort is going to be 2 over 3 times 5 over 6 becomes 10 over 18, which is 5 over 9. Okay? Which is kind of an amazing thing, right? The normal inverter has a delay of 1. Yes?
Why do you do 2 and 0.5 and then say?
I make it symmetrical, right? Basically, I say, well, this is double. From an overall driving strength, this has double the driving strength that I really have from a normal inverter, which would be, if I would have a 2 to 1 inverter, right, that's the normal inverter. From a pull-down perspective, pull-up perspective, this is double the strength. So what I'm going to do is I'm going to divide by 2, and I divide all my capacitance by 2 to basically give you the equivalent driving strength. And that's why my capacitance basically is so small. Remember the definition, right? It's the logical effort is total capacitance that I see at the input of my node for a driving strength which is equal to a minimum size inverter. So I could do the opposite thing, right? It says here's a minimum size inverter to give the same driving strength. I'm going to make all the devices actually smaller. So this is 4 to 1. I'm basically now going to divide this whole thing through, and that's what I'm doing. I divide this all by 2, and I get 2 and 1 and 0.5. Right? The nice thing about this thing is that we only worry, so we make it asymmetrical. And the only device I worry about is the top one. I don't care about the bottom one, what it does. So I care about the top one, and I'm going to make sure now for the top one I have the same driving strength. So I divide it by 2. That basically becomes half in that particular case. But the beauty of this thing is this is amazing, right? I make a 2-stage logic family. One of them consisting of an inverter, and the other one is dynamic gate. And if I look at the total logical effort of this whole thing, is smaller than a normal inverter, even though there's already an inverter in here. Which is show why dynamic is a good idea. You actually make a inverting, well, it's actually a double inverter, it's basically a buffer. You have a buffer which basically has a smaller logical effort than a normal CMOS inverter. Even though it's 2 stages. Kind of bizarre, isn't it? But it's because of the fact of that skewing thing. You know always what transition is going to take, and you optimize only for that transition, not for the other one. Okay? So that's this. Now, the next question is a little trickier. Okay. Suppose now that, remember the optimal fan out, right? So it's asked what's the optimal stage effort of a dynamic gate like this. Suppose now I start chaining those guys together. Right? You have stage 1. I have an inverter. I go into the next one. So I really create a chain of buffers. Right? There's another inverter, and so on and so forth, and you go to the end. And then I say I have a certain load capacitance CL here, and this is my input capacitance CI here. Okay? So the question is now, what would be the optimal stage effort for every one of those stages? Okay? Remember, for inverters, it becomes, depending upon the gamma factor and things like that, but basically it becomes about 3.6, right? That's what you would do. Every stage in the optimal case would go up with a factor 3.6. You make them larger, larger, and larger, and larger, and that's going to basically give you the optimal delay type of respect and also determines the number of stages. So here, logical effort is a little bit more complicated because we don't talk about logical effort. Basically, stage effort is actually equal to fan out times logical effort. Where for an inverter this is equal to 1. Logical effort is smaller here. So if you know it, go to the complete chain and solve it and say, okay, here's what's going to be the optimum number. It's going to be a little bit different. But you can write down exactly the same equations. You write down your total stage, your total fan out F. Right? We know that's CL over CO over CI. You know what the total path effort is, which is a product of the logical efforts times basically the fan out factor. So you get total fan out F. And you figure out what the optimal number is per stage that you should get. And you will see it's a somewhat different. It's actually not 4 anymore. It's a somewhat different number with the dynamic logic. Because of the fact that this logical effort factor comes in here, which you don't have when you would have normal inverters. Actually, the load that every stage has to drive can actually be a little bit larger. You can imagine, right? For an inverter, you do a factor 4. But if I basically make it easier to drive the next stage, because I have a smaller logical effort, I can drive for the same delay a little bit larger capacitance. So if I would build a buffer with dynamic gates, I'm going to get away with less stages. Because every gate has an easier job of charging capacitors. Because remember that, right? Logical effort is how hard do I have to work to charge a capacitor? Complex gates typically have a larger logical effort, so they have to work harder to charge a capacitor. But here you have a gate which has a smaller logical effort. It's easier for that gate to charge a capacitor. So you can imagine that every basically of those things can drive a larger fan out. So it's going to be more, not 4, but maybe 4.5 to 5, depending upon that logical effort thing. And logical effort, was it? Was it 510? No. What did I come up with? So actually, you should find the number right away. It's 4 times that number of that logical effort factor. That's really what you're going to get. Right? So that's question number 2. Question number 3 of this exam is not relevant because it's on, I think it is on, actually it's a fairly complex layout question. I don't think it's something I would like to ask. Here's a last question, is about power dissipation of complex logic. This is something you should be able to solve, but it's actually a good example of doing some analysis. So you have a function f equals a times b plus c invert. Okay, single logic stage, a plus b and c. No, small variation, a plus bc. Okay, good. So what it says is assume, okay, standard CMOS logic. You assume that the probability of A is equal to 0.1 and the probability of B equal to 1 is 0.5 and the probability of C equal to 1